And the next couple of talks are going to be focused on that.
Okay, thank you. So I'm going to try to keep you awake for the last half hour of this very long day. Last year, I reported some results on decision making, what I generically call it graphical cognitive architecture. This year, it finally has a name. It's now called Sigma. And I'm going to report on two new aspects of it that are quite different. One, reinforcement learning, which is the basis of this talk, and the other, mental imagery. The point in both of these talks is not going to be that these are great reinforcement learning or mental imagery algorithms, or that they're particularly novel, but the relationship of them to the architecture itself. That's the main kind of results out of these particular papers. So let's look at this. So here's the goals of the work. The general goal here is to approach general intelligence via graphical models. Now, you've seen a lot of different graphical approaches to intelligence today. These are going to be different from any of those that you've seen, and I'll try to explain a little bit how they differ. And if you want to ask more during the panel, we can go into that in more detail as well. But graphical models are the main opportunity I'm trying to leverage here in building Sigma. So we're trying to build a new cognitive architecture or system called Sigma. There are three desiderata that are driving its development. In this talk, I'm only going to focus on one, functional elegance. Essentially, how does one provide a broad scope of functionality from a simple and elegant base? I really do want to come up with something like cognitive Newton's laws, if possible. That's one of the big ways that the approach I take to architectures differs from much of what you'll see. So we'll see trying to do the same kinds of functionality as OpenCog or other systems, but not by piecing together a bunch of existing systems, but trying to derive most of that action from a simple, elegant, theoretically elegant base. That's the goal, at least. Whether it's possible or not is still remains to be seen, though there's some interesting results showing the potential. So here's a cartoon I used to exemplify this based on SOAR. This is sort of what SOAR was like when I was involved. A fairly simple architecture, broad functionality, but there were issues. So John Laird and his group have continued with SOAR. In SOAR 9 have, pushed by functional needs, have developed a considerably more complex system. What I'm trying to do, again in cartoon, is to return to something that is comparable to the old version of SOAR in simplicity and elegance, but which actually has a superset of this kind of functionality. So that's the goal of functional elegance. Now in this particular talk, the idea is to extend Sigma to reinforcement learning. It's a key concept in both intelligent robots and AGI, but I want to avoid adding it from whole cloth. I don't want to just program in a reinforcement learning mechanism and start adding up all the learning mechanisms in the architecture. What we're going to do is deconstruct in terms of existing mechanisms in Sigma, and then only add minimal changes to those mechanisms as necessary. That's sort of the methodology. Okay, for those of you not familiar with reinforcement learning, here's a simple animation explaining it. The basic idea is to learn the values of actions for states, such as left or right in this simple 1D corridor, based on propagating backwards rewards that you receive in states during exploration. Here's one form of the equation where you're trying to learn these Q values of actions on states. There's a learning rate parameter, there's a discount factor, so you're discounting future rewards as you come back to now. So the robot explores a little bit in my very fancy animation. It sees a reward in each of these states. It finally gets a reward where there's a state where there's a reward it cares about, and then essentially propagates those backwards in a discounted fashion to learn how good those actions are. Very roughly, that's what reinforcement learning is about. Okay, so we're going to base Sigma on graphical models. So what graphical models are fundamentally about are not graphs. They're fundamentally about efficient solution of complex multivariate functions by decomposing them into products of simpler functions. It turns out you can then map those decompositions onto graphs and solve them efficiently on those graphs, reflecting the semantics of the overall function you're trying to solve. So there are a number of familiar forms of these. You might know Bayesian Markov networks, Markov random fields, all those kinds of things. Bayesian networks are a particular form that are about decomposing probabilistic functions. Factor graphs are about decomposing arbitrary functions. Now, what's particularly interesting about graphical models from an architectural perspective is that they yield a broad state-of-the-art capability from a uniform base across symbols, probabilities, and signals. Essentially, everything is the same algorithm. At least for these kinds of state-of-the-art algorithms, when cast in this kind of a formalism. So it provides the possibility for a single uniform base that yields a whole bunch of state-of-the-art capabilities on top of it. Now, you then solve this by some method, usually full-form message passing, such as summary product, which is the same as loopy belief propagation, or sampling algorithm, or variational method. And you can support mixed and hybrid processing, so symbolic and numeric, discrete and continuous. And it turns out that several neural networks map onto them. Not all of them, but some of them that fit this particular kind of decompositional semantics. Sigma is based on factor graphs, so something like this, and the summary product algorithm. So, very quickly, what the summary product algorithm does is compute marginals on all the variables in the graph, or the mode of the entire graph. You pass messages. The messages here are always distributions over the variables on the link. Starting with evidence at particular variables where you know what the value is, here it's 3, here it's 2. And then you combine these at the nodes via particular rules. At variable nodes, you do a pointwise product. At factor nodes, you do that, including the function there, and you summarize out any unneeded variables. Usually with something like summary integration or with max. Yields different kinds of things depending on what you're doing. Okay, so we pass messages, they get processed in this way, and eventually we have a marginal on the function for y, given the evidence. Roughly that's how it works. So here's an example more in the sigma way. That was an algebraic equation. This is a form of semantic memory based essentially on a naive-based classifier, where given evidence about particular features, like you know that something's alive and it has 4 legs, you want to be able to retrieve or predict. It's basically the same thing. The category here that it's a dog, plus values for the features that you want provided. So this is again a form of generalization, partial match, not done in a discrimination network fashion, but done via a naive-based classifier. So to do that, you need prior probabilities on the concept. This is what's called a conditional. This is the knowledge representation used in sigma. I'll explain it a little bit more in the next talk. It's not that critical for this talk. But that then gets compiled down into a subgraph of a factor graph. You also need conditional probability distributions for each of the features given the category. That is then another set of conditionals. You put that together and you get a rough structure that looks like this with the concept, the different features, which are different types. And this gives you the graph representing the semantic memory with this set of features. If you then assign evidence, like that it is alive and it has 4 legs, it propagates according to the rules of summary product. That predicts a dog, which then comes down and predicts these other things, all by the rules of how these graphs work. Now, it turns out further that it's possible to define simple, local, incremental learning algorithms on these graphs based on gradient descent that can do a variety of interesting forms of learning. So we've implemented one based on an article from the mid-90s in Bayesian networks and adapted it to what we're doing with factor graphs. The basic idea actually is that the messages coming back into these functions is in fact the gradient that you want to learn from. And so each time you get a message in, you can learn a little bit, and you do that over and over again. And depending on the kind of function and the kinds of messages coming in, you get the different kinds of learning that you're looking for with a very simple mechanism. Now, we're extending this mechanism, we might replace it with others, but the key thing is this local incremental aspect of the learning. And it's a very simple mechanism, and it fits in very naturally here. It took me about 2 hours to implement the first version of it. It actually turns out to be similar to backpropagation in neural networks, but you don't need a separate backprop phase because messages are passing in both directions here, and in fact the messages are already coming back in here that you need to learn from. So roughly this is the kind of stuff we've been doing in Sigma. You've seen a little bit of that. I'm going to focus on that, and the next talk is going to talk about that. But you can see there are other kinds of things we've at least started to get some results on too, including things like perception, again in these same graphs. Okay, so reinforcement learning in Sigma. We're going to learn values of actions for states based on an equation like this. The idea is to deconstruct it in terms of this gradient descent learning mechanism, plus knowledge for prediction. So we're going to have conditionals that predict the current reward, the discounted future utility, what you expect to see in the future, and the action preferences, the cues. So these will all start out uniform. We'll have some backup knowledge, and define a transition function that tells us what state we should get into, given the current state in the action. We then want to learn to predict distributions for the reward, the future utility, and cue. From the reward itself, and the predictions of these, so I won't go into the details of how that works. But that's the basis for it. And so that actually lets us do reinforcement learning in Sigma without changing the architecture at all. You add the right knowledge in, leverage gradient descent and the processing and summary product, and it does it. And it turns out with one change to the architecture, it's a fairly small one, we add essentially a new decision cycle in the middle of the decision cycle, if you think in terms of cognitive cycles. It can then learn the action models, these transition functions, at the same time it's learning reinforcement learning with the same learning mechanism. It can also do model-free reinforcement learning. So here, roughly, here's just a way of looking at some of the knowledge. Here's the uniform distribution over the rewards to begin with. This is the knowledge for doing the backup. This is a uniform distribution over the next states and the transition function. So we can learn a reward function. We can learn the cue, which says basically that when you're to the left of the goal, go right. When you're to the right of the goal, prefer left. We can learn projected future utilities, where this is the goal and you never do anything from there, so there's no projected future utility. And we can learn the action models, all uniformly. Okay, it turns out these graphs are all the expected values, but learning is actually full distributions. So in some sense, there's more power here than you'll see typically in reinforcement learning. Okay, I don't know how long I've taken, but I'm just about done. So basic message here is we're able to deconstruct a version of reinforcement learning, essentially on policy. This is like SARSA rather than Q-learning, if you're familiar with those. Model-based reinforcement learning in terms of the existing mechanisms in Sigma plus knowledge. And with the minimal extension, we can both learn the models and do model-free RL. It turns out that's useful for other things as well, including work with COM-DPs and so on. But much more is clearly required for a full and fully useful RL capability. So it's a beginning, but it shows that essentially can come out of the architecture. And it's added in a function elegant manner. Overall, some of all of this kind of stuff has been added on top of factor graphs, degradient descent, piecewise continuous functions, which I'll explain in the next talk, and so on. This can be viewed as mapping onto a form of Occam's razor, Newell's exhortation to listen to the architecture and how to decide how to develop architectures further, and to bring in a local Oxford reference, David Deutsch's call for explanations with reach. Sigma is still fairly new, but I think we're starting to see that there is a chance to achieve these desiderata, especially this functional elegance one, which is the one that's counter to the way most people think about how to build architectures. Okay, so let me go right into the next talk. Okay, so this is extending mental imagery in Sigma. So again, we've got goals. That's interesting. That's not interesting. What the hell happened here? Let me quit PowerPoint, restart it, see what happens. Now it's behaving differently, but oh well, it worked, of course, 2 hours ago. All right, I can talk over this. So again, we've got we have the three desiderata. We have the functional elegance still here. The one that we're adding in this particular talk is grand unified. So there's a notion of a unified cognitive architecture where you bring all the cognitive aspects together, and they mutually support each other. They work together well. And together they provide the capability we need. I wanted some name for what happens when you go beyond sort of the strict cognitive and you have perception, motor, emotion, motivation. There are a number of people working on bringing those into cognitive architectures, but often they're not considered strictly cognitive. So I've floated this notion of grand unified architecture, just like people talk about grand unified theories in physics. Doesn't mean that Sigma is the only form of that, but it's an attempt to come up with a term for what people are doing when they go beyond the cognitive in trying to do integration in these things. So this one talks about that because we're going to be talking about some more perceptual kinds of information in addition to cognitive. And again, we're going to try to do it in a functionally elegant way. This is the kind of stuff you need when you're going to virtual humans and intelligent robots. This is the kind of thing we do at ICT, virtual humans, but clearly many people also do intelligent robots. This is not good. Hopefully it doesn't exist beyond this slide. So the particular thing here is to extend Sigma's capability for mental imagery. ability to represent and reason about spatial information, and it's a bridge between perception and cognition, so that's the brain unified aspect. It is implemented uniformly with both perception and cognition. That's the functional elegance aspect. All right, hopefully we're past that problem. So if you're not, no we're not, because there's an empty bullet there. I could reboot the machine, or we could just see if we can get through it. Okay, so mental imagery, for those of you not familiar with it.
Maybe the elephant ate the missing text.
Yeah, maybe the pink elephant. So mental imagery is sort of mental representation of spatial information. If you're trying to solve the 8 puzzle, you might have a representation of the board in your mind. If you're trying to do some of these classic psychological 3D rotation tasks, you'll have in your mind something. It might not be exactly that 3D thing, but you'll have something that you're representing to do it. So you have questions like, how do you add and delete objects from images? How do you, I don't even know what I intended to say there. So let's see. Aggregate combinations into new objects. It shows it's still on the slide. Translate, scale, and rotate them, and extract implied properties for further reasoning. This is the kind of stuff you want to do with mental imagery. Now, in symbolic architecture, you've either got to represent and reason about this stuff symbolically, which is sort of the traditional AI approach to doing, or you connect to a separate imagery component, as SOAR 9 has done. So there is an imagery model in SOAR 9, but it's a separate component that does this, and then you pass things back and forth with that. The goal here is to use the same mechanisms that we've just seen, for example. Representation, I'll introduce the piecewise continuous functions that are in Sigma, and reasoning based on conditionals, graphical models, and a couple of special kinds of nodes. I'll talk about affine ones and not filter ones in this talk. All right, so piecewise continuous functions. It's a unified representation for continuous, discrete, and symbolic data. So I'm not going to talk about symbolic versus sub-symbolic, but I do care about numeric, both continuous and discrete, and symbolic. If you want to think of this as sub-symbolic, you're welcome to. Okay, at the base here is multi-dimensional continuous functions with one dimension per variable. They're going to be approximated as piecewise linear over a range of regions. So here's a conditional probability distribution of the weight of an object broken up into regions, given its category. And you can see each one has a linear function, it can be degenerate, a linear function of its weight. So with that, we can approximate arbitrary continuous functions as closely as we desire, if we have enough regions. But we can also discretize the domain for discrete distributions. This is the number of legs given the category. And then we can Booleanize the range and add a symbol table for symbols. So this represents that object 01 is brown and alive. The architecture works with these continuous functions. All of this is sort of stuff we put on top for us to look at. Okay. It's analogous to implementing digital circuits by restricting an inherently continuous underlying substrate, and it's used for both function representation and message representation within the graphical models. Okay, so I've mentioned conditionals a couple of times. These are the basic long-term memory structures. And they're a blending of the concepts from rules and probabilistic networks. And they're a deep blending of them, so you don't just get one or the other, you get mixtures of the two. And there are patterns like these joined with an optional function. Here's a function. Patterns can be conditions, actions, or context. Conditions or actions are just like those things you're familiar with in rules. With conditions, messages flow from working memory. Actions, they flow to working memory. Contexts are essentially the natural thing in Bayesian networks, in probabilistic reasoning and constraint networks. They involve bidirectional information, combining essentially local match and global influence. Now it turns out that really the main difference between these in the graph is just which direction you pass the messages. But depending on that, you can get conditions and actions, or you can get these contexts which deal with general probabilistic reasoning. Functions are then defined over variables in these patterns, and then they compile down into these graph structures in particular ways. Okay, so I did that on the previous talk, so just remember Sigma's factor graphs and summary product. And then I want to focus on one particular class of nodes here, which are particularly relevant for mental imagery. These are affine transforms. Now what they are is they're special purpose optimizations of standard factor nodes that operate on the boundaries of regions in these piecewise continuous functions. So we can do translation by adding or subtracting the boundaries. We can do scaling, shrink, enlarge, and in fact reflect in various ways. And we can do rotations, currently only by multiples of 90 degrees by swapping dimensions. And I'll show you a little bit more how all of that works. Okay, same slide you saw before. This time we're talking about mental imagery. This is from previous work. This is the new work. This is why it's extending it, because there was some previous work at Vika last year. Or like how do you pronounce it? Okay, so 2D imagery buffer in a puzzle. So normally in AI we represent the A puzzle by things like cell 1 is left of cell 2, tile 1 is at cell 1, and so on. What we're going to do here instead is represent the A puzzle more by a hybrid 3D function. So there are two continuous dimensions for x and y, and a discrete dimension for tile. Okay? This just goes from 0 to 3 for the spatial and 0 to 9 for the tile. Then that defines essentially a plane for each tile, and the region which is gray, which actually has a value of 1 functionally, is where the tile is located. Okay? So these are continuous, and the tile covers this whole region. It's not a discrete thing there. Okay, we can then translate a tile by offsetting the boundaries. So this tile is here, and we want to move it over into there. This is the conditional that does it. It uses these offsets, this +1, which isn't just adding 1, it's really translating an entire function by 1. So what it does is it's going to translate it by 1, and then it's going to pad the new region and crop the old region. And now you can see that it's sitting right there. Now, this is just an optimization of what factor nodes can already do, but it turns out that you need certain kinds of delta functions to do this directly with standard representation. Those aren't very well representable in the kinds of piecewise linear functions we have now. So what we've done is provide these specialized nodes that do this directly. So you can do this kind of optimization down below in terms of that third desiderata I haven't talked about, sufficient efficiency. So just some other examples. This is a Z-tetramino from the game Tetris. So you can scale it in half horizontally in place by a transform like that. You can reflect it horizontally, again in place, that's why the 4 is in. The minus is where you get the reflection. Or you can rotate it right by 90 degrees by swapping the variables, so y goes to x, x goes to y, and again we have this 4 minus, partly for the reflection and partly for the keeping it where it was. So these look just like standard rules, except for they're operating on mental imagery based on these kind of affine nodes. We can also do composition and extraction of objects and features from images by making use of the summary product algorithm, plus a few other things. So for example, this is a conditional which says, okay, we have an image and we have a variable here, so we have a whole bunch of objects over locations x and y, and we're going to have a composite which is independent of the objects. So we're going to summarize out all the objects. Now we're going to summarize them out by max here, and I'm not going to go into the reasons, but that happens automatically. So we're essentially taking the max over these individual objects, and we generate a composite image, which is now another object that we can deal with any way we want to. We can do things like overlap detection. Here it's just making use of the product aspect of summary product. So we have this one which matches here, we have this object which matches there, and then we get something here which just generates the overlap of them by the product. We can do edge extraction. Here's this composite. What we've done here is we've translated it by a small amount, and then we've inverted it, it's a negated condition, so that everywhere that was 1 is now 0, everywhere that was 0 is now 1. And then we AND those, product them really, and we get the edges. So we're doing edge detection without actually ever having pixelated this. The size, the width of the edges is just a function of how much we do the translation there. So you can see this really is a continuous representation. You can do other things here. You can find the topmost object by making use of those filters I didn't talk about, and other kinds of things as well. So these are things that help you then extract properties for further reasoning based on manipulations you've done of imagery. Okay. Conclusion. So we've got 2D mental imagery from Sigma's core representation of reasoning capability, piecewise continuous functions, conditionals, negations, affine transforms, and filters, It turns out that all of these are used in reinforcement learning except negation. One of them seems like a robot learning task, this seems like a cognitive spatial reasoning task, but they use the same mechanisms within Sigma. And it's closely integrated with cognitive processing, essentially usable with all numeric variables. Whether you think of them as mental imagery or not, it could be time, it could be other kinds of variables. In fact, I use it for the state hierarchy when doing reflection. I use it for episodic memory with time. All of those use some aspects of this mental imagery aspect. And much still remains to be done. And I won't go into details on it, but again, this is sort of the beginnings, or at least this is the second step on this kind of capability. And just want to show you, so we've seen a bunch of humanoid robots. These are the kinds of virtual humans we work on at ICT, and the goal for what we want to try to use Sigma for. We want to try to integrate the capabilities required. These are tour guides at the Boston Museum of Science. This is a entertainment, mixed reality, Old West scenario. These are both military. This is multi-party cross-cultural negotiation. This is counseling of a soldier with issues. So those are the kinds of virtual humans we want to eventually put Sigma inside of. And that should do it. Thank you.